interactive, and international science stream. The theme for today's stream is ELELEMT, and we'll see 4 performers from 4 different European countries to prove you that talking about chemistry in an interesting way goes way beyond just flashy explosions. Let me introduce our tonight's guest. First, joining us from Bulgaria is Nasko Stamenov. Nasko,
hello,
can you hear us? Hi. Hi, how are you doing tonight?
I'm fine, thank you.
Thanks. And can you tell us a little about what you have prepared for us tonight?
Well, it's copper, so if you like the color blue, this presentation is the right for you.
Oh, well, that's great. Thank you very much. And next, from the Netherlands, Mark Bette. Hello, Mark. Can you hear us?
Hello. Nice to be here.
Thanks. Perfect. And what can we expect from you?
Well, I found an article about a Chinese lab that developed a process to make graphene, and I made a school experiment of this.
Mm-hmm. Great. Thank you very much. And third, coming from UK, is Michael Londesborough.
Well, good evening. I'm not coming from the UK. I'm actually coming from the Czech Republic. And this is my lab where I specialize on research on my favorite element from the periodic table. It's the 5th element, and that's the element of boron. And you're going to be learning with me a lot about the beautiful 5th element, boron.
Thank you, Michael. I hope we made sure that in the subtitles you're titled correctly UK and Czech Republic.
That's right.
And last but not least, coming in from my right side, actually, is Adam Blahák. Hello, Adam.
Hello, hello.
And what element did you choose for tonight's experiment?
Yeah, I choose uranium.
Okay, thank you very much. So we have all different elements for the streams, and we are so excited to have you all here. Thank you very much for coming, and I'll get back to the audience. So please have in mind that this is an interactive stream. And what makes it interactive is you. So we are streaming to many different platforms, and on any platform that you are watching us, you can go to the comment section and ask questions, interact with the questions from our performers, and you just make this stream. So this is it from the introduction. I hope we will all enjoy tonight's ELELEMT. Welcome back, Nasko.
Hello.
Okay, so we all know, and our audience will see it, that you are very passionate about chemistry. And I would like to ask you, was it always the case, or did you find your way to chemistry at some point in your life?
Well, I find my way to chemistry at some point of my life. It was at 1st grade. My parents had bought quite a lot of encyclopedias when I was a little kid, and I did the mistake to read them all, so then I was really, really hungry for science.
Thank you very much. Okay, and so we are ready for your performance, so please, stage is yours.
And I'm going to show you one of my favorite copper experiments. Of course, we are going to use the salt of the copper. This is the copper sulfate. In my country, it is called blue stone. And it is the most common copper salt in the world. You can find it with no real problem anywhere in the world. I'll get my bottle of water and we're good to go. So first I'm going to make a little nice solution of copper. And as you can see, I don't really care if all the copper is dissolved, because actually I need concentrated solution for one thing at the end. But let me just pour a few test tubes of the real nice blue copper sulfate. So, what can copper sulfate be used for? Well, copper has the tendency to make complexes, which means that copper can react with molecules that contain oxygen and nitrogen and combine with them, bond with them. And this will actually change color and help us see things. For example, if I have an ammonia solution, ammonia is a nice molecule with nitrogen and unpaired electronic couple, and combine that with our copper sulfate, we'll get the nice deep blue color of what is called the Schweitzer reactive, or Schweizer reactive in German and in Swiss. Well, this means that if it touches anything that contains such nitrogens, it should become such color. So what I have now is some gelatin. And gelatin is a protein. And proteins are made out of amino acids. And amino acids, of course, contain the exact same nitrogen atom that is connected with 3 bonds to stuff, and it has the unpaired electronical couple. So when I mix it, it's not the deep blue that we expect. Why so? Well, ammonia, of course, is basic. It's quite basic. Amino acids, not so much. So I need a little bit of a base. And what I have here is a little bit of sodium hydroxide. And I'll drop some of the sodium hydroxide, a strong base, into that mixture. And lo and behold, when I mix them together, because my gelatin, of course, start to gellify everything, when I mix them together, you see the nice, cool color of nitrogen and copper. Beautiful. Did I mention that this is my favorite element? Well, yeah. So, what I have now is some iron wool. Iron wool. It is used usually to clean up really nasty burned pots. And what I'm going to do with it is I'm going to dip it in a nice solution of copper sulfate. Well, iron is quite the more reactive metal than copper, which means that the iron atoms will become iron ions, and the copper ions will become copper atoms, which means that when I take it out, you'll see a change of color. My iron has covered with something that is really nicely pinkish brown, and this is the color of pure copper. And if I put it all in and mix it about and swirl it around, what is going to happen is that you're starting to see that my solution actually becomes different shade of grayish blue. And actually, it doesn't show perfect on the camera, but it starts to get green tint. This is because most of my copper is going to react. And if I take now this thing, you'll see that most of it is this nice color. So I leave that be, and we'll talk a bit about the last experiment. And for the last experiment, I need a little bit of salt. And I told you that this is blue because the water has bonded with the copper, and we have nice complex of water and copper. But now I'm going to pour some salt, which will give quite a lot of chlorine ions. And what chlorine does is it also wants to bond with the copper. So what happens is that our solution actually becomes green. But there is more. What is going on now is here in my stock solution that still has some crystals of copper sulfate. I'm going to pour quite a nice amount of sodium chloride. And my solution will become really dark green, which you may see as gray-green by the camera if I see correctly. But it is nice deep green. And what's coming next is my favorite part, because I'm going to take that cup and put it in here. So I want you just hold that cup in front of you. What I'm going to put in there is some metal that is more reactive than iron, and now the copper solution is more reactive than before. So we have two things that are more reactive to react with each other, and this is aluminum foil, and I've made a nice ball with it. I'm going to drop it into the solution. And at first nothing special happens, it's just that the aluminum foil little by little starts to change color. The same brownish copper that I showed you before. But the more it reacts, the hotter it gets, the faster it reacts, and the faster it reacts, the hotter it gets. So, listen. You hear sizzling, you see bubbles. If I show you the cup here, you'll be able to see even some steam. This is quite an exothermic reaction, and I really like that one because only with stuff from the market and from agro-apothecary you can make some quite nasty stuff. And this is why I'm holding right here, because the temperature of that reaction is way beyond 100 degrees. All right, I've showed you one of my favorite experiments about my most favorite element, and I hope that you enjoyed the time with me. So I'll see you afterwards in the discussion, and have a great time with the other guys.
I'm back here now with Adam.
Yeah, hi.
Hi, Adam. And I've heard, and even from you, that you've been on a trip.
Yeah, I have.
You've been on a trip in Mongolia and teaching kids about science and English in Ulaanbaatar. Is that correct?
Yeah, near to Ulaanbaatar. I was in a little village called Shuvu Fabrik. It's 40 kilometers away from Ulaanbaatar.
Great. And do you have any interesting, preferably short, story that you could share with us today?
Story? I don't know. But we are going to talk about radioactivity. And I have there my Geiger counter also. So I find 3 hotspots, some little higher radioactive places there. So it's quite interesting there.
Great. And is there somewhere?
Yeah, it was near to Ulaanbaatar. There is a hill or mountain called Tsetsegun, and it's like a sacred, sanctioned, or how can I say that?
Sacred hill. Okay.
Sacred hill. Yeah, the mountain.
It's radioactive.
Yeah,
Sacred and radioactive.
Yeah, also. Those invisible forces are there. Yeah.
Yeah. Okay.
We can.
Yeah. Perfect. And then the stage is yours.
All right.
So please, it's up to you.
Yeah. So I ask for darkness. So we turn off our lights, and we will look for 2 things. I hope for 2 things. First thing is here, maybe. This is our cloud chamber. If you look really closer, you can see there little lines, what is radioactive particles, what are shooting from our samples. But we are looking for bigger samples here next to our cloud chamber. Yeah, this is 1 piece of uranium ore. And if we shine with a UV light on it, we can see a really nice color. It shines with green color, and here is also some reddish color. The red thing, it's not uranium, it's some kind of calcite, but the green thing, it's some kind of uranium mineral. If you look to our uranium sample, it's right here. It's just a boring stone. Yeah, you can see it's just a black pieces of stone, nothing interesting, but we use it in many fields. And here comes the first question for you: where we can find uranium? In nature or in some artificial products? It's up to you. So type it into comment, and we look on it in a minute. But first we'll look for our uranium ore. If you can shoot it a little bit closer. Yeah, you can see there are little bubbles, bubble-like structure, and it's very typical for this kind of uranium ore. This uranium ore I found on a first date with my girlfriend in Příbram. Příbram is Czech city, famous with uranium mines. And we can measure it, actually. Yeah, because radioactivity is everywhere around us. I have this Geiger counter with me, and it shows that there are 0.3 something microsieverts per hour, or 0.5, something like that. Nothing high, nothing what we could be afraid. But if we put it close to our uranium stone, it's a lot higher. Yeah, it's higher. Yeah, this is quite a dose. It's something like, it should be something like 500 microsieverts per hour. So it's quite active, quite radioactive. And this little clicking sound, this is radioactive particles which are shooting to our detector. And if we look closer to our uranium sample, we can see a nucleus. And that's a really important part of our radioactive physics, nuclear physics. And what happened in our uranium sample? This is one nucleus of atom of uranium. And there is some protons, this is the whitish things, and the black things, this is neutrons. And as we know, I think the uranium is unstable. So it shoots 2 protons and 2 neutrons away, which we called alpha particle. Yeah, here it is. And in this case, it changed. The element changed. The atom have changed, because element is based on atomic number, which means the number of protons there. But the number of protons have changed already. So now it's not uranium, but now it's thorium inside. And it shoots this like little, quite big particle, alpha particle. And we can look on this particle with a special camera, which can show us the radiation. This is it. Yeah, we can. Now we have it even the screen. Yeah. Now nothing interesting is there. Maybe some particle radioactive now and there. And now we put it closer to our sample. And we can see that a lot of things are happening here. Yeah, it's quite amazing. Ha ha ha. And if we stop it, we can see that there are some bigger. Here is some bigger particle. This is the alpha particle, what we are mentioned earlier. But what is the rest? The rest is beta particles and gamma particles, and gamma radiation and beta radiation. And it is caused by another element, which are radioactive and what are daughters of our uranium. Because thorium is also radioactive, unstable, and it radiates not alpha particles, but beta particles. So one of its neutrons changed to protons, and during this change, the electron is emitted. So this is the beta particle. And now it's no longer thorium, but it's protactinium. And the protactinium is also radioactive, and it decays in a decay chain. We can show our decay chain, maybe. Ah, yeah, here it is, here it is. So here is the start, here is our uranium, and decay to thorium, then protactinium, and it goes like this to the end, which is here, and that's a lead. Nice, we can close it. Thank you very much. And now we are going to talk about one of the elements which is daughter of our uranium. But firstly, I have a... No, firstly, yeah, I show it to you. Yeah, that's what I want to do. This is things where is polonium, which is created by a decay of uranium. There should be a polonium 210, so it has 210 protons and neutrons. And it was created in USA in 50s. And this is a fire plug with polonium, a radioactive element. This is something what is written on the box. And if you put our Geiger counter nearby, you can notice that nothing really happened. It's decreasing, so maybe it's not really radioactive. And here comes the second question from me to you. Why didn't we measure anything? There are three possibilities what could happen. The first thing is that our device can't detect this kind of radiation which is emitted by this polonium thing. Or the second one is it stopped being radioactive somewhere in history. It's no longer radioactive. Or there is a third option that it was just for marketing because it was cool to have everything radioactive. So the salesman decided he will write that this spark plug is radioactive. So, right answers A, B, C. And now we can look for answers where we can find the uranium. What do you think? Jáchymov, yeah, that's a quite famous Czech uranium mine, already closed. Yeah, Dolní Rožínka, that's also the mine in Czech Republic. Our last opened mine, but it's already closed now, a few years. And, all right. And we can find uranium also in some artifacts, some things like atomic bombs, maybe. Or the big thing now, energetic, the nuclear power plants. There's also uranium used. But we are looking for some special things, and we are going to look to history. And in history, uranium was quite popular for coloring things, like some ceramics or glasses. Yeah. This green color is colored by uranium. It is a nice green color, and if we put it to UV light, but we need a dark first. Yeah. If we put it under the UV light, we will see that this glass colored by the uranium shines nice green. Yeah, the best thing I think is these buttons, yeah, for some shirt. Uranium glass buttons. But we used uranium not only for green color, but also for orange one, red one, black one. It was really popular for coloring ceramic special. This was one used in history, and I have something really interesting what I think it is. Yeah, turn on the lights, thank you. And uranium and all the radioactive samples was quite popular in history and medicine, maybe some cosmetic also. And in Czech Republic, we there was manufactured some radioactive uranium soap. So in history, like in 20s or 30s, we was creating this soap, but I have only the box. So it's kind of a weird part of our history, I think. And now we can look for your answers. What about the spark plug and the polonium inside? What do you think? Do you have any? Yeah, the B. The B was it's no longer radioactive. Okay. Any other idea? C. So it was only for marketing. Okay. Yeah, the marketing purposes. Okay, and other? Do we have an other answer? C also. Yeah, the Shimon thing double. Yeah. For two people. Okay, the right answer was B, because it was probably radioactive. I hope so. So there was a polonium, but polonium has a half-life something like 130 days. So after 70 years, I think not many polonium is there. All of it is lead now, I think. So the right answer was B, so our viewer is right. So thank you, and I can pass the screen to others.
Thank you, Adam, very much. Welcome, Mark. And when I saw your presentations and performances, I really enjoyed that you used a lot of props. And you were able to add a lot of comedic aspects to it, which was a lot of fun. So I wanted to ask you, have you ever considered to be a magician?
Oh, no, I haven't. No, sorry. But I during my lessons about burning experiments, I do flash paper, so I have a little bit magic tricks in my lesson.
Yeah, I think it would be a great magician. So anytime you would consider it, I would be there to see you. Okay, thank you. And we are all ready to see your experiment, and the stage is yours.
Thank you very much. I'm going to tell you something about graphene. And for the people who do not know graphene, it was discovered in 2004. And the people who discovered graphene got the Nobel Prize in 2010 for this discovery. It's 200 times stronger than steel. It's a great electric conductor, and so on, and so on, and so on. So all over the world, people are searching for a way to make graphene on a large scale, because then they can make a lot of money. So I found an article about a lab in China that had developed a process by calcination of calcium carbonate with magnesium to create graphene. So they used an oven. The oven was filled with argon, and the oven was heated till 850 degrees. So at that point, the calcination started. So you can see that during the process in the oven at a temperature at 850 degrees, the calcination of calcium carbonate starts, and calcium oxides and CO2 exist. The CO2 will react with magnesium and form magnesium oxide and carbon monoxide. And the carbon monoxide will react with magnesium, and then carbon will show up. Carbon was examined, and it turned out to be graphene. So they have discovered a way to create graphene. So the chemistry behind this whole project is more or less similar to the curriculum that we have in our country for the school exams, chemistry. And the good thing was I have all the chemicals in my classroom. The only problem that I had was I don't have an oven which is filled with argon. So I had to find a way to create enough heat for this calcination. So I thought of using an excess of magnesium, because when you burn magnesium, the temperature can rise till 2200 degrees. That should be enough for this calcination reaction. So I tried that, and it turned out it worked. So I have created a school experiment which I can demonstrate in my classroom, and I can demonstrate the principle behind this experiment from China. For me, this is very important to announce, because I don't want to give the impression that I can make graphene with this experiment. I only can demonstrate the principles behind this process, because we all know that carbon can have different structures, and you have to have the right circumstances to create graphene. And in my classroom, I don't have those circumstances. So again, I'm not pretending to create graphene, I'm demonstrating the principles behind. So during my school experiment, I use calcium carbonate, and I use 1 spatula of calcium carbonate, put it in a porcelain dish, and then I use an excess of magnesium. So in this case, I will mix 2 spatula magnesium with my calcium carbonate, and I will make a mixture of it. And I will demonstrate this, I will show this mixture to my students, because they have to know, they have to see that the mixture is light gray. They have to know that, because we learn them if we have a chemical reaction, they change the, for instance, color or so, then we can see it's a chemical reaction. So they have to see the first starting material. So now there's enough heat for this calcination, and this is the process that takes place. And this is the result. And you can see there's a big difference between the starting materials and the materials after the reaction. I did bring a result. You can really see it's very dark. So there should be carbon in it. So during my lesson, I will ask my students to answer these questions. So they should be able to describe the starting and the ending substance. They should be able to describe the reaction phenomena, explain which phase magnesium has in the oven, it's molten, explain why the oven is filled with argon that doesn't react with other chemicals. So they have to make the reaction equation correctly. They should recognize molecules, salts, and metals in these reactions. So now I have a new problem in my classroom with my students, because we have a mixture of 3 solid chemicals, and I want to separate the carbon from this mixture. And the question to you all is, how can I separate the carbon from this mixture? Oh, nice. Centrifuge would be interesting. I think it's. I think there is a way that is easier than centrifugate. So I hope that my students will recognize calcium oxide and magnesium oxide as a base, like acid base. So I hope they will recognize it as a base, and then they should answer that I have to use an acid. And in this case, I will use hydrochloric acid, because when it reacts with the mixture, calcium oxide will react to calcium chloride, and the magnesium oxide will react to the magnesium chloride. Both are salts that are very good soluble in water, so they will solve into my mixture. So now it's an interesting thing, because there's also a gas in this reaction. You can really see there's a lot of gas coming from. You saw that there was a gas, and I want to know if you can answer the question, which gas did appear? So we have a couple of options. I can't read. The first one is hydrogen. The second one is oxygen. The third one is carbon dioxide, and D will be helium. Thank you, David. Correct. B, okay. Thank you, Daniela. A. Thank you, Janet. Thank you, Lucy. A. Okay, very nice. Thank you very much for answering this question. The thing is, when I have used an excess of magnesium, and the magnesium will react with the hydrochloric acid, hydrogen will be formed. If there still is calcium oxide in this mixture because it didn't react or because I used an excess of it, carbon dioxide will be in this reaction. So two gases are possible, hydrogen gas or carbon dioxide will be another possibility. I have now a mixture of a solution from calcium chloride and magnesium chloride, and in the mixture is a solid carbon structure, and I have to separate this from this mixture. So the next question is, how do I separate it from my mixture? So you saw it already on the movie. Of course, we use filtration for this process. And after the filtration, this will be the results. So you can see a lot of black material in the filter, and this is carbon. So for me, this is a more or less a simple experiment with a lot of chemistry in it, and that's why I'm very enthusiastic about this experiment. It's very good for the students to think with you as a teacher. You can ask the right questions, and then you can train the children in their chemistry. So for me, this is a very nice experiment. And I hope that you all also will be very enthusiastic about this experiment, and you will do it in your school also.
There's actually one question coming from me, and you mentioned that you do not claim that you create graphene, you're just exploring the principles. And what would it actually take to create graphene? And under what conditions can we use these principles, this experiment, to create and produce graphene?
Yeah, so in the experiment that the Chinese people did in their Chinese lab, you really have to have a good temperature, because my temperature, 2200 degrees, is much too high. They go to 850 degrees. And it's very important that during this process, the magnesium melts, because then it forms a very thin layer on the calcium carbonate. And then you will get also the thin layer of the graphene. If you do it like my process, you will get more graphite, I think, I assume. But the circumstances are not good enough to make graphene. So the temperature is very important, and the molten position of magnesium is important.
Yeah, thank you very much. And I can definitely enjoy your students I can definitely imagine your students enjoying this kind of lesson. So thank you very much for demonstrating this. And we are here. So if we have a question, we have time for one more question from the audience.
I thank you. What a very nice question. Yes, I do, because the possibilities with graphene are huge. I did read one thing that was very nice, because they can make little holes in the graphene structure, and doing that, it enables people to take salt seawater, pour it through the filter that you created, the graphene with the holes, and then you have drink water. So making the drinking water will be very easy if we have a lot of graphene. So yes, I'm really fond about graphene and the possibilities. Yeah.
Mm-hmm. Thanks, Lucia, for the question. Thank you for answering that and introducing graphene and its applications and experiments to us. And we are ready to continue. We've seen 3 performances, and we have one waiting in line. But as we have a discussion session later, we are approximately in the middle of the stream. So please stay tuned, continue interacting in the comments, and we are ready to continue. And Michael, welcome back on stage.
Thank you.
And as you've mentioned, you are now in Czech Republic. You are affiliated with Czech Academy of Sciences. And sorry, I forgot, what's the town called where your lab is located?
So my lab is in a small town called Rzesz, which is about 15 kilometers north of Prague, on the banks of the Vltava River.
Yes, thank you. I remembered, sorry, I just wanted to hear you saying that. But what I wanted to actually ask is that you gave presentations and performances a lot of different settings, right? I mean, you gave presentations and science shows in larger or smaller audiences, but you also have to defend your work in academia. And also, I mean, you're the one who hosted the Prague Science Stage. And I definitely saw you on television at least once. So from all of these different settings where you can present, where do you feel most comfortable?
Oh, well, I think I get different feelings and different benefits in different scenarios. So working in front of a camera for television, that gives me sort of a thrill of the studio, the lights, the pressure to get it right, and that's very much different to when you're in a live performance where you have this interaction and energy with the audience. Each has a different sort of characteristic, and each one is very sort of is fantastic in its own different way. Perhaps though, I suppose my favorite is really to have that live performance, that contact with the people, the energy in the room, the adrenaline of the live performance. I think that's maybe the best.
Yeah, I can imagine. Right now you are in your lab, right? So you won't get that energy from the interaction, but we hope we will get interaction through the comments. So please, now stage is yours, and we are so excited to see you.
I'm going to talk to you a bit about my favorite element of all the possibilities from the periodic table. My personal favorite is actually the element next door to carbon, and that's boron, this little beauty. So you can see the 2 important numbers associated with boron. You've got the number 5 here, which is, of course, its atomic number. It's how many protons an atom of boron has. That's why it's the 5th element. And but the second number here is the total number of the total mass, the atomic mass of the average boron atom. And it's not a whole number, it's 10.8, which is interesting. That means it's got a number of, 2 isotopes. So most of boron is found with 5 protons and then 6 neutrons, which would bring up to boron 11. But 20% of the time, 20%, which is a large fraction for a light element, it has a second isotope, boron 10. And that's a very important isotope, which has all sorts of other applications, which I'm going to come to shortly. But boron is a really unique element in the sense that it's not made in the usual way. And when I say made, elements, the lighter elements in particular, certainly all the way up to iron, are made through nuclear synthesis in stars. So in the cores of stars where we get nuclear fusion, where lighter elements are compressed and they overcome the repulsive forces to squash together and to form new, gradually heavier and heavier elements, all this occurs in the stars. And but in the case of boron, there's no mathematical way to get to the fifth element. You can't add up gradually the heliums with more hydrogens with more heliums to eventually get to boron. So it's really a puzzle that it exists at all. And it exists, in fact, in a similar way to how uranium exists. It requires a supernova. It requires the star to explode to really generate enough energy to fragment a lot of the heavier atoms and recombine these elements into other forms. And from these huge events, you can get boron. And eventually some of that will be in the nebulous, which forms planets like our own. And thanks to that, we have boron as well on this planet. And we find boron on this planet as we find most elements as an oxide. Here's a sample of boron oxide. Like most things, it's a white powder. But boron oxide has quite an interesting history in terms of what people have done with it over the ages. So these salts of boron oxide that we find, they were called borax, and their first uses were found by the ancient Egyptians. And the ancient Egyptians found mines of borax in what is today's Turkey. It was then part of the Hittite Empire. And they discovered that these borax salts were very good at desiccating, at extracting, removing water from things. And it became very useful to the ancient Egyptians for the mummification of bodies, in particular pharaohs, of course. And so it became a very expensive and important material for this ideal way of desiccating the body quickly, removing the water to ensure a perfect mummification process. Later on, ancient Romans, they discovered when they were making glass, that's because, of course, glass like this is mainly silicate, so it's mainly silicon oxide, sand. But they found that, well, if you add a little bit of borax, a little bit of boron, then the actual properties of the glass somewhat change in that it becomes far less fragile. And in particular, it can cope with huge temperature shock. So I've just poured here the coldest substance that we have readily available for us. That's liquid nitrogen. So that's minus 196 degrees. And that thermal shock, though, is not enough to make this glass crack. And that's because of the boron that's in this silicon oxide, which is implanted there. If you add a bit of borax salts into the glass mixture when you're heating it up, and that gives this wonderful property. And indeed, to today, the use of borax salts into various ceramics is a very important and part of how it's marketed and how it's sold into the current days, markets, and how boron figures in our industries. But what I want to concentrate on today is something that happened in 1912. You see, 1912 is a year that, if you've seen the film Titanic, where the great ship Titanic sank. And on that same year, well, there was a person who did a remarkable bit of chemistry. He managed to replace the oxygen in these borax salts with hydrogen and form, thus, the first boron hydrides or boranes. And in fact, my first question to you today is which chemist synthesized the first boranes in 1912? Anyway, the chemists who did manage to do this, he discovered really a new boom in inorganic chemistry. This is the gentleman here, Alfred Stock, a genius. He also did some amazing. His supervisor, PhD supervisor, was Emil Fischer. He did some amazing work in organic chemistry. He also announced to the world that it's a shame that our planet has this remarkable process of photosynthesis, which is unique to carbon, which turns the oxide of carbon dioxide, into a hydride of carbon, and hydrocarbons, which of course are the be-all and end-all of organic synthesis of our beginnings and life and color and everything on this planet. And he was keen to set his PhD students, the best of which was Alfred Stock, to look into these other elements. Are there other elements that can form a series of hydride compounds? And Alfred Stock came up with the hydrides of boron, the boranes. Now, you've seen in the previous talk some of the structures that carbon makes. They tend to be these flat, ring-like or chain-like structures. Well, Alfred Stock realized and found out that boron, with its hydrides, form these amazing three-dimensional, very beautiful, what are called polyhedral structures. Here's a 12-vertex icosahedron. And so these boranes suddenly began to increase in their number, more and more synthesized, and they realized that boron, after carbon, is the element which has the greatest potential to form hydrides. I want to talk about and show you what some of these hydrides can do. Okay, so here I've got, what I'm going to do is going to put this little dish in front of me here. I've got a small amount of boron hydrides here dissolved in a solvent, and I'm going to pour it out here onto my plate carefully, because in the same way as hydrocarbons are very useful to us as fuels, well, it didn't take long before the boron hydride chemists discovered that boron hydrides also oxidize in air. But when they do so, and I hope you can see that nicely, it gives a wonderful big difference to if I burn carbonaceous materials in oxygen, we get this orange flame. Whereas here, if I take the boron hydrides, they give a wonderful green flame. Now look at that. And often actually during some of the major projects which were developing boron hydride chemistry, they called those projects the Green Dragon. Now, it didn't take long before they recognized they could calculate how much energy is being given off via this oxidative process with boron hydrides compared to carbon hydrides, which were the fuels of the day. And they realized that, and they calculated, and they also measured that this oxidation process of the boron hydrides is giving off much more energy per unit volume than if I use hydrocarbons. Well, that led to a big boom. What happened next? Because you see, now we're talking about the 1930s, 1940s, 1950s, and it was all about, let me get this the right way around, it was all about trying to find rocket fuels. So here in the Czech Republic, in Rzesz, where I have my labs, there was some top secret research work looking into the boron hydrides as a potential new rocket fuel. Now, I'm going to show you how we can go from an oxidation process, an easy one, such as we've just seen here with the burning of boron hydrides, and ramp it up to actually get a rocket propulsion. It's not actually that difficult and something you can do in your schools or even at home if you're very courageous. And indeed, you don't need a lab like mine to be able to make the boron hydrides. Borax, the salts of boron oxide, can be found in many different products that we find at home. They're often in washing powders, for example. And if you dissolve borax, salts of boron oxide, in alcohols, you can form these boron esters, which have a similar effect. If dissolved then and burnt in alcohol, you'll also get that nice green flame. Now, in any oxidation process, especially with the boron hydrides, which are releasing its energy, which are in these bonds, so you've got your boron hydride molecules which have these wonderful polyhedra. All the energy is trapped inside these bonds. And when you get oxygen coming through, you begin the burning process, you're forming new molecules of boric acid, boron oxide, and water. And that reaction is very quick, very fast. All the old bonds are breaking and new bonds are being formed. And that's releasing the energy difference between the older bonds and the new bonds as the energy is being released. And if that reaction happens quickly, then we get a big expansion of gases which are being produced, and that expansion of gases can act as a reacting force and a propulsion force for a rocket. So all we need to do really to make a rocket and make some rocket fuel is to have the right chemistry, as we have here, and then you just need to force those new molecules of gas that have been formed to go through a small area and therefore create a propulsion force. So this is essentially all you need to make as a rocket. You just need a bottle with a cap. Now the cap, I've just put a hole in the middle there. Can you see the hole there? You can see the hole there, right there in the middle. Well, that hole is what I'm using to really confine the space, to force these molecules that have been formed inside our rocket to come through, to really push through this confined area to come through. So that's how I can get the propulsion force. Then, so inside my rocket, all I do is I put a bit of fuel. I don't need much at all. I'm going to shake it a bit. I'm going to use my hand just to warm this boron alcohol mixture up, just to get the transition to vapors, so it's mixing with the air a bit better. On the top here, I've just sellotaped a simple straw, because I'm going to use that to guide the way my rocket's going to fly. And I've got along here a simple piece of string. Push it through like that. Okay, now I just need to empty my bottle of the remaining fuel carefully onto the floor. I'm going to go back over here. Okay, it's all tight and ready. Now, hopefully you can still see this. I'm going to take my fuel over here. I'm going to take my lighter. Are you ready? Can you see it all? Ready? Countdown. 3, 2, 1. So that's it. We got the propulsion that we needed. That rocket really did fly. I only needed a very small amount of my fuel, the boron fuel. And I want to explain, though, how eventually the borons didn't become the rocket fuel of choice. And that's for the following reason. When I burn hydrocarbons in oxygen, I form carbon dioxide and water, both of which are gases that can leave the engine of the rocket without any sort of deposition of anything. Whereas when I'm burning boron hydrides, I'm forming water, but I'm also forming something else. I want to show you it here. Here, can you see it on the camera? See that white? That's boron oxide. So the oxide of boron, whereas the oxide of carbon dioxide is just a gas that would leave the engine of the rocket. Well, when we use boron fuels, the problem is you get accumulation of boron oxide, and it's a white powder. And that white powder will eventually stop the rocket from working. So you get a lot of initial energy and a lot of initial acceleration, which is superior to normal rocket fuel. However, the accumulation of this white powder destroys the actual trajectory eventually. Nevertheless, I think even Elon Musk's SpaceX thingy rockets, they do use a little bit of borons at the beginning to get the initial thrust. But to finish with, I want to show you, of course, today's rocket fuel that's used. And today's rocket fuel is Today's rocket fuel is none other than, almost broke the dishes there. There's another, and what I've got over here, here we go. This is today's rocket fuel. It's, of course, hydrogen gas. And hydrogen gas gives a wonderful oxidative reaction, which you're going to know, and you'll probably be familiar with. Let me just position this balloon in the right place. Let's get it onto the floor. Here we go. Now, this, don't try at home, kids. What I'm going to do here is I'm going to just show you the real rocket fuel of today. It is, of course, oxidizing hydrogen to give water and a lot of energy. 3, 2, 1.
Michael, it was such an enjoyable experience to watch you talk about your favorite element. And I must say also informative, because boron, I guess, from the elements that we saw tonight, is the one that we learned the least in our lifetimes. So this, I guess, was very informative for a lot of us. And do we have a question from the audience? I'm asking the studio. And this is not a question, but I don't know which part, because we saw a lot of things blowing up. But yeah, this is good, hobby. A question? No, not yet. So we probably will hear some questions during the discussion session, and we can then move on to the discussion as we heard, and we will get to all the questions that we did not get to during the performances. And also, I hope we will get some discussion going in between our performers. I'm looking forward to it, and we're getting it to now. Okay, so now that we've seen all the performances, I welcome back on stage everyone. Adam here, Nasko, Mark, and also Michael that we saw just recently. And now I would like to ask the studio if we have some questions that have not been answered yet, so we can see them. Okay, so we have one from the account My Favorite Experiments through YouTube. Does the reaction usually go to completion so that there would not be both magnesium and calcium carbonate left when you mix with acid? That is a question to Mark, I guess, right?
That's a very good question. Thank you for this question. I'm not sure, because you saw in the picture that the result in the porcelain glasswork is black and white, and the white material can be calcium carbonate, and it also can be, of course, it's magnesium oxide and calcium oxide, but probably also some calcium carbonate. So I cannot guarantee if all the calcium carbonate reacts and all the magnesium reacts. No, sorry.
Mm-hmm. Okay.
Good question.
Yeah, thank you for the question and for your answer. Is there any other question from the audience? Okay, I guess we've received one question from Michael directly, and I think it's best that you ask it yourself.
Yeah, I was very impressed with the that sort of homemade synthesis almost of graphene. And you mentioned at the beginning, of course, one of the many interesting properties that chemists are trying to develop with graphene is its conductance, is its electrical conductivity. And I was wondering, did you do anything with what you separate, what you actually made? Did you try any sort of conductivity experiments?
No, I did not. And that's because in the Netherlands, we have a clear line between this is chemistry and this is physics. and in our country, electricity is physics. My goal with my students is I want to show them some possibilities with the chemistry, with the experiments. They have to understand what we can do with some products, but the level of my students is not the highest level in the Netherlands. So I also have to compromise with what I teach and what I do not teach. I think that if I had a group with a higher level, gymnasium, for instance, then I probably would ask them find a way to control if there is electricity conduction here.
Because what you could do, you could just smudge a bit on a piece of paper, and then if you create a simple circuit with 2 wires to an LED, and one's linked to a battery, and then there's a break in the circuit which you can then put the 2 wires on either edge of the smudge on the piece of paper, and then you can see whether if the LED lights up or not. And you could compare that to, say, for example, graphite from a pencil, smudge, or others.
Yeah, good suggestion. I promise you, if you will be the speaksman again on the science on stage and I will be there, then I will have done this experiment. I promise you.
Good man.
Okay, thank you very much, Michael, for asking that. And we have one question from the audience. And Sven is asking, Michael, are there any specific uses of the different boron isotopes?
Yes, very good question. And indeed, I wanted to come to that. At the beginning, I mentioned it very briefly, but time was running out. It's actually linked, the importance of the different boron isotopes are linked to one of the previous talks this evening, and that's with uranium. So uranium, one of the many uses of uranium is, of course, in nuclear fission reactors. So because of the sheer size of uranium with its, I don't know, is it 92 protons and I don't know how many neutrons, it's so massive, it's so unstable, or at least some of its isotopes are so unstable, it has a tendency to fall apart, as was demonstrated with alpha particles coming out and all that kind of thing. And if that fission reaction, that can lead to, the generation of large amounts of energy, which is the basis of nuclear fission energy that we're using in our reactors to generate electricity. And that reaction is propagated by neutrons. So for every uranium nucleus that falls apart, that fissures, it releases 3 neutrons. And those 3 neutrons go to start further fission reactions. And so you get an exponential growth of the fission reaction. Now, if you want to we need to control nuclear reactions so it doesn't get out of hand like it did in Chernobyl. So, and to control nuclear reactions, nuclear fission, what we do is we need something that can absorb these neutrons. So if you imagine if the nuclear fission of uranium is propagated by these neutrons, if we can absorb some of them, we can control the rate at which the uranium will fissure. And the perfect thing for that is boron 10, not boron 11, but boron 10, because boron 10, of course, is quite happy to take a neutron to become boron 11. So that's one really important use. So it's really important in the nuclear industry. The second thing is that a similar process, boron neutron capture process, can be useful in medicinal context. It can be used for the treatment of certain tumors, cancerous growths, which are on the periphery, on our which can be easily got to, and the sense that you can irradiate boron 10 isotopic containing materials, and they will take on that neutron, and they will begin then a new process, sort of almost like a transmutation into lithium, and that can destroy the cell in which it's located. So what isotope of boron is being used is really important. It's also actually really important in the lab when we're using different spectroscopic techniques and also mass spectrometry to actually distinguish between different different compounds we might have. And that gets quite complicated. But the fact that we have these two different isotopes gives us almost like handles on which we can explore the structure of boron compounds even better.
Thank you very much. And I would like to ask Nasco now. And Science on Stage was mentioned a few times already. And I would like to ask you simply, what was your experience with Science on Stage this year in Prague?
Well, it was a really, really nice experience, though. It was my third time going to Science on Stage. And this time I saw quite a lot more projects because I got the time for that. And quite a lot of new stuff that I haven't really tried before. So yeah, and of course it was my first time in Prague, which was wonderful. Prague is really, really nice city. But the point is that quite a lot more people were quite well. It felt like more people were eager to speak now. Because of course we had a little bit of pandemic going on, so most of the teachers there were looking like they really wanted to go out of their country and come there and talk to other people. So it was one of the best Science on Stages I've been to.
Great, thank you very much. And I think I've seen a glimpse of Michael's question to Adam, I guess.
Really?
Is that correct? Oh, maybe it's just something else. What was it you, Michael, asking?
Is it Adam? I'm sorry, I'm not very good at remembering.
Yeah, Adam.
The gentleman standing next to you is Adam.
Yeah.
Adam, you had you were showing us your Geiger counter, which can count all these subatomic particles being ejected from radioactive elements. And I was wondering, what is the most radioactive fruit or vegetable that we eat?
It is a Brazilian nut, I think, or banana. Yeah. But I think Brazilian nut have more potassium 40 than banana. So I think Brazilian nut.
Yeah.
Or mushrooms, because mushrooms have a lot of heavy metals inside, or could be there. So some kind of mushrooms from certain areas, it also could be radioactive.
So
do you when you go to eat at a restaurant, and you want to have mushrooms or fish or whatever, do you take out your Geiger counter and check out?
Yeah, not really. Didn't try that yet.
Okay.
Well, it's an icebreaker in a date, isn't it? Whipping out the Geiger counter on a date.
Yes.
Yeah.
Great. I think that's all the questions from the audience. And I know that, Mark, you have one experiment that you did not have time to perform during your performance. Do you think you could show it to us now?
Yeah, no problem. If Alice can open my PowerPoint presentation, then I can demonstrate it. A little bit further in the presentation. Further. Yeah, stop. So it's about the chemistry about samurai swords. You can go to the next slide, please, Alice. So if you start the first movie, yes. So the first thing is we bend a hairpin, and the students have to remember how much force they use for bending this hairpin. Then they have a second hairpin. They have to make it red hot, and then they will cool it down very quickly in cold water. The water is 18 degrees. Probably the temperature in the metal, it will be 1400 degrees more or less. So they cool it down very quickly. Then Go on, please. Oh, you have to continue with the movie, Alice. This is too quick. Yes. Okay. This is the moment where the second hairpin is red hot, and now we will cool it very slowly in a yellow flame by lifting it up. And we use more or less 20 to 25 seconds to lift it up and cool it down very slowly. So now we have two hairpins, one cooled very quick and one very slowly. And then we have to examine the difference between the hairpins. So the first one, they have to bend again and compare the power. But this one breaks. The second one bends more easily than the original one, and this whole process is used in a samurai sword because first, what happens with the first material, the first metal is heated and then cooled down very quickly, and the metal that is formed there is martensite, and martensite is a very hard material, very tough. So if you want to make a sharp samurai sword or knife, you use a hard material, in this case, martensite. But if you hit with your sword a very hard object, then your sword will break. And you don't want a broken sword, especially when it's 30,000 euros. So you don't want it. Then you have to use a metal that is more bendable if you want to keep the sword alive. But if you use a sword that's bendable, you can make it sharp, but it will not stay very sharp. So during the process of making a samurai sword, the makers of the sword use both techniques to make the two metals that we saw here. So they put on a thin layer of clay on the side that has to be sharp, and a thick layer of clay on the side that have to be bendable. Then they heat the material till red hot. And after this material is red hot, they cool it down in water. And on the edge, where was a thin layer of clay, the cooling down is going to be very quickly. So there will be martensite, hard material. And on the other side, with a thick layer of clay, the cooling down is slowly, and there another material is made, and that material is bendable. So this process can be demonstrated with a very simple hair clip process with a beautiful story about how they make a samurai sword. Thank you, Alice.
Yeah, so we had to finish it once we had it.
Yeah, okay, I know.
Thank you for this additional demonstration. And as we saw again in a very simple object, as you see it in a finished product, there's a lot of chemistry going on during the process. Great that we can have some experiments that get us closer to the chemistry of it. And also, what I liked about this demonstration is that even a hairpin, and of course, the torch, can be a science prop, right? Yeah. And my question then would be, I think Adam already mentioned that he has his science prop, that the Geiger counter, always on him. So maybe I would ask all of you then, do you have any kind of science props that you always carry with you, Nasco?
Well, in my pockets, you can always find some salts and pieces of metal and strange rocks. So yeah, I don't have a favorite science prop, but in my backpack, you can use to make a science show or experiment in any case. It's just there.
Yeah. Okay, thanks. Michael?
Well, something I always have in my pocket. I'm not sure. A lot of the things I have are usually pretty big. They're too big for my pocket. But I generally have in my pocket a little bit, a stash of gun cotton. That's pretty good and effective. You know, if you soak 100% cotton buds or gauze or something like that in a mixture of concentrated nitric and sulfuric acid, and then you neutralize with, I don't know, sodium carbonate or something, and let it dry, then you form what's called gun cotton, which is nitrocellulose, and that's extremely flammable, and it burns without any smoke or anything. It's very effective. It's good to show kids. You can just put some in your hand and light up, and it goes. Whoosh. So that's pretty good to have, I think.
Yeah, I can imagine. Mark, do you have any favorite props that you carry?
Most of the time I have flash paper with me in a €10 note. So it's more or less the same as what Michael explained about gun cotton, but it's the same material. But this is paper. So I have a €10 note, and then I can light it and then throw it away, and then no smoke, no nothing. The flame goes high and then it disappears. That's what I usually have with me.
Yeah, I think I saw you in similar demonstration, but you took a note from an audience. Is that correct? But you don't light that one up, right?
No. Okay. Yeah, I did, but what I did with that note was we did the note in a alcohol water mixture, and the mixture is 60% alcohol, 40% water, and we put a little bit sodium chloride to it. And when you then dip it into the mixture and burn it, only the alcohol will burn, and the water cools down the paper, and the sodium chloride gives a very nice orange flame to it. So yes, we did burn also paper money from the audience, but they got it back.
Yeah, that's perfect. Perfect scenario. Okay, and I would like now to ask Adam. And it was already mentioned, I think it was Mark who mentioned that in Netherlands, and I think it's the case in Czech Republic as well, that the science subjects are taught separately.
Yeah,
so
physics and chemistry.
Physics.
Yeah. And biology also, yeah.
But also, when we saw the experiments, we saw there's a lot of all of this stuff going on at the same time, and you are not chemist.
Yeah, I'm not a chemist.
Yeah, so... But we saw that you can be in a chemist show because even in physics of radioactivity, there's a lot of chemistry. And when you work with kids, is it hard for you to actually talk in a more complex manner because they are used to separating these subjects, or do you find it easy to just say like this is the transition between chemistry, physics?
Yeah, I try to combine everything. Not only the science subjects like the chemistry and science and biology, but also a little bit of history or politics. In uranium, there's a lot of politics. So you can also talk about that. And about history and uranium, you can talk about politic prisoners in mines in our last regime in Czech Republic. So it's also interesting thing to combine everything and put it more into wide perspective.
Yeah, I think it's great that children have places like these, like that they can learn in the whole complexity of things, not only in the narrow subject. And as you mentioned politics, I don't want to end political, but I have one question gets to a little bit political, and that is that I find it a great challenge now in the era of social media and short attention span to have an effective science communication. And I would like to ask all of you, what do you think is the best way how to maneuver in this era of short attention span and be an effective science communicator? And I would like to start with Nasser.
Well, of course, one thing is to branch out. You can, if you have a type of presentation that you're familiar with, and you go through it and go through it and go through it, and not so many people go about it and go and see you, then you need to branch out, try new stuff, go where people are. Go outside, go into some social media that you know your students are interested in. So just just go about, spread your wings and try to find where the people are.
Thank you. Mark, can I hear your thoughts on this?
I think it's a very difficult question because honestly, I'm not happy with social media, not at all. But it's in our community, so we have to deal with it. But I'm not happy with it. But if we have to deal with it, the communication that we have should be short, enthusiastic, to the point, and then you will have the most effect, I think, on using social media.
Yeah. Adam, do you have any thoughts on this?
Yeah, I tried a lot of broadcasting during the COVID era, the restriction. So I tried to use social media as a speak to children and students. And I think that it's not our purpose to change their mind and change their behavior of the children, but we should show them the path in social media. The nice thing about social media, what can be used for more connecting world and to spread the wisdom and knowledge.
I mean, social media is all about algorithms, right?
Yeah, it is. Yeah, it is.
So we can exploit the algorithms by giving good content and
it's also true.
Yeah, creating pitfalls, scientific pitfalls, educational pitfalls. And also, Michael, can I get your thoughts?
Yeah, I think a lot of what Adam says makes a lot of sense, and I agree with him, both on the perspective of trying to combine lots of different disciplines into one, that sort of holistic approach. Certainly in terms of research work, definitely we're having to become more and more multidisciplinary. You would find it very difficult to publish in good journals if it was just chemistry. I'm combining all the time with physics, biology, etc. So you need that approach. And I like the concept of also putting in their politics, putting in their art, putting in their drama, whatever it might be. I think what makes very effective communication is it's, to a large extent, it's all about enthusiasm, and it has to be genuine. When you're talking about things, it has to be people switch on if you are genuine, if your enthusiasm is genuine. Then people want to listen. When it comes to social media and audiences and low attention spans, I think also what Adam says is also true. You can't sort of force feed somebody who doesn't want to listen something which you want to create. Just create something which you enjoy creating, and the audience finds it or it doesn't. And there's going to be a group of kids, people, whoever, who will take the time, who will watch the content, who will be inspired by that, and who will go places. We don't need everybody to become a scientist. It would be great if more people, generally speaking, became more interested in science. But if somebody hasn't got the attention span to last a couple of minutes, then it's their fault and not yours.
Yeah. Okay. Thank you very much for your thoughts on this, and also for the whole stream. I mean, my last question would be to the studio, if we have any unanswered questions from the audience, and if not, which is the case, I would like to again thank you for the performances. It was such a pleasure to have brilliant science communicators on stream, live, interacting with the audience, and we can see it works even when the COVID is over. And again, you can follow us on social media. You can follow us everywhere you watch the stream. And we prepare streams every few months. Even the Czech stream will start in the 29th of November. And you can definitely look forward for another international stream in the spring next year. So again, thank you very much for the night. And I wish you great rest of the night, and that you take a lot of inspiration from these performances. So good night, and hopefully see you soon. Bye.
Oliver.
Bye-bye.
Bye-bye.
Bye.
Bye.